Okay, let's unpack this thought experiment.
Welcome to the deep dive. Today, we are wrestling with a question that uh, really sits at the intersection of pure ambition and, well, computational physics.
It really does. It's this desire for total personalized control over a foundational AI system.
Exactly.
Our listener posed this beautiful, really pure engineering question. If you wanted to build an automatic speech recognition system, an ASR system, something like Whisper, but from the ground up.
Right, from scratch.
Totally from scratch. Tailored only to your voice, your specific accent, your very specialized technical vocabulary, and even your unique Hebrew and English code switching patterns. The question is, what would that actually entail?
It's this idea of completely bypassing fine-tuning, just starting from absolute zero, training a model exclusively on your own personal audio data.
It's the ultimate build versus buy problem, but, applied to deep learning.
It really is. Instead of leveraging the, 500,000 hours of public data that giants like OpenAI have already processed, you're proposing to start with just random weights.
And trying to create this bespoke encyclopedia of sound and language, using only a single person's voice as the input.
It sounds kind of epic when you put it that way.
It does. So our mission today is clear. We're going to dive deep into the monumental gulf between that theoretical from scratch fantasy and the highly efficient, mathematically proven reality, which is, of course, transfer learning and fine-tuning.
We need to get into the weeds on this. The architectural reasons why fine-tuning isn't just a shortcut, but actually the only correct engineering approach for something like personalization.
And then we'll give you the concrete steps. Down to the sample rate and the file format you need to execute this project perfectly.
We'll spend a good amount of time contrasting the astronomical requirements of foundational model training, the millions of dollars, the months and months of training against the elegant, practical solutions offered by modern transfer learning.
And the contrast here isn't minor, is it?
Oh, not at all. It's the difference between...
Okay, let's ground this in the real world then. When OpenAI built the original Whisper, what was their starting line? What was the data volume they were working with?
The scale is almost hard to grasp. The original Whisper model was trained on 680,000 hours of audio data.
680,000 hours.
680,000. To put that into perspective for you, that is continuous audio playback for almost 78 years.
78 years, wow.
Yeah, and this massive data set wasn't just random audio. It was explicitly collected to cover 98 different languages, thousands of diverse accents, and all these critical domains, from clean studio broadcasts all the way to extremely noisy, reverberant, real-world conversations.
78 years of continuous audio. That alone really puts the initial data requirement into stark relief. But okay, let's simplify it. Let's say you wanted to build a foundational ASR model that was just for general English, not multilingual. What's the absolute bare minimum data required before a model starts to exhibit any kind of generalized intelligence?
Even simplifying it down to that, we estimate the minimum viable scale for a decent generalized ASR foundation is still somewhere in the neighborhood of 100,000 hours of diverse, high-quality transcribed audio.
100,000 hours. And when you say diverse, that's the crucial part, isn't it?
That is the most crucial part. You need audio covering at least 10,000 different voices and speakers.
Okay, but why so many? Why so many different voices? If I'm only training it for myself, why do I care about 10,000 other people?
Because the model has to learn generalization. That's the entire game in machine learning. It needs to learn that, for example, the English phone tag sounds completely different when it's spoken by a woman from Texas versus a man from London or a child from Canada.
So it has to separate the concept from the specific instance of the sound.
Precisely. It needs to decouple the underlying linguistic concept, the letter T, from the specific acoustic characteristics of that person's mouth shape, their accent, their pitch, the quality of their microphone. Your model has to learn what speech is as a general concept, not just what your speech is.
Without that massive diverse foundation, it just can't filter out noise or cope with tiny variations in pronunciation.
It has no reference point. It's like trying to learn what a dog is by only ever seeing one single Chihuahua. You'd be very confused when you saw a Great Dane.
Right. So if our listener provides their hypothetical personal data, and let's be generous here, let's say 10 hours of really high-quality audio, we are comparing those 10 hours against a minimum requirement of 100,000 hours.
Or the actual Whisper baseline of 680,000 hours.
So that 10 hours represents, less than 0.01% of the minimum viable knowledge base.
It's an insignificant drop in the ocean of general speech knowledge. It's not even a rounding error. The model simply does not have enough examples to establish the fundamental rules of sound and language. It's statistically impossible.
This realization alone should probably stop the project right there. But let's keep going with the thought experiment. Let's assume someone, somehow, manages to source 100,000 hours of transcribed audio. The data cost itself must be just staggering.
Oh, it is. We estimated that just transcribing that 100,000 hours, even at the lowest commercial rates, would cost you somewhere between $600,000 and $6 million.
$6 million.
And that depends entirely on the quality and the complexity of the audio. Transcription is the hidden monster cost of building any kind of foundational ASR. It's a huge human effort.
And then comes the compute. Even with this theoretical mountain of data, the hardware and time requirements are, I'm guessing, enterprise grade.
Absolutely. Training a massive transformer model is only feasible with high-end interconnected GPUs. We're talking a minimum cluster of 8 NVIDIA A100 GPUs, and that scales up very rapidly to 64 or even 256 GPUs for optimal speed. An individual using a single desktop or even a modest local server, you can't even get on the field.
And for a Wister scale model, so about 1.5 billion parameters, how long are we talking, even on that really high-end cluster?
You're looking at months. Training that 1.5 billion parameter model on 100,000 hours of audio, even with a highly optimized setup, would take at least 4 months of continuous, uninterrupted training on an 8x A100 cluster.
And that's 4 months if nothing goes wrong.
If nothing goes wrong, yes. And that continuous operational cost is what just kills any individual budget.
Right.
It really does. Using current cloud compute costs for that level of hardware, the compute alone for those 4 months is estimated at around $690,000.
So you're talking millions of dollars just to get to the finish line of a general model.
And that's not even accounting for the human capital, the data engineers, the machine learning researchers, the infrastructure people you need to keep that cluster running for 4 months straight.
So, okay, the conclusion is crystal clear. Building a general ASR foundation from scratch is prohibitively expensive, it's incredibly time-consuming, and it requires astronomical amounts of diverse data that no individual can realistically collect or process.
Exactly. But now let's look at the more catastrophic scenario, the one that really settles the argument for good.
Okay.
What happens if the listener ignores all of that advice and does train that massive architecture, but only on their 10 hours of personalized audio?
Right. This is the moment of truth. What is the result of applying a gargantuan hammer to a tiny, very specific nail?
The result is catastrophic overfitting. And it sounds dramatic, but it's a technically accurate term.
So what does that mean in practice?
It means the model, given its massive capacity, all those 1.5 billion parameters, and its complete starvation of data, finds the easiest possible way to minimize the error on the 10 hours it sees.
Which is?
Pure memoization.
So instead of learning any general rules about my voice or my language, it essentially just creates a perfect dictionary for those 10 specific recordings.
Precisely. It fails to generalize because it hasn't learned that decoupling principle we talked about. So if you said the word serverless in a low tone on Monday during the recording, and then on Tuesday you say serverless again but in a slightly higher tone,
the model has no idea what that is.
It will classify Tuesday's sound as complete gibberish. It hasn't learned the variability of your voice. It has only learned the exact spectral signature of the Monday recording. It's brittle.
So even with the same speaker, any new recording that deviates even slightly from the training set, different microphone placement, slightly different emotion in your voice, a minor change in speaking rhythm, the model just completely falls apart.
Completely. You might get 100% accuracy on the specific training samples it memorized, but on any new piece of audio, the word error rate, the WER, would skyrocket. It would likely hit 85% to 95%.
So it's outputting just noise or completely unrelated words.
Yeah. It becomes a system with zero actual usability.
It's the technical equivalent of trying to write an entire textbook on theoretical physics, but you're only given 10 pages of specific biographical notes about Einstein to work with.
That's a perfect analogy.
The architecture has the capacity to hold the entire textbook, but the input only provides those 10 pages, so it just memorizes the 10 pages perfectly.
That is exactly it. So the conclusion we have to draw is that training an ASR from scratch for personalization is not just difficult, it is fundamentally the wrong architectural and data strategy. You have to start with the foundation built by the big labs, and then you specialize.
Which brings us to the smart way of doing this, the fine-tuning advantage.
Right. If the fantasy of training from scratch is built on, impossible scale, the reality of fine-tuning relies on the elegant efficiency of transfer learning.
We're leveraging all 680,000 hours of that generic knowledge, and then we're just making it locally optimal with our 10 hours of personal data.
That's the idea.
But the paradox is still a bit challenging for new users, I think. How can my 10 hours of personal audio not just completely destroy the pre-existing foundational knowledge? Why doesn't the model immediately forget everything it knows about general speech the moment it starts looking only at my voice? We hear the term catastrophic forgetting all the time.
And that's a real danger. That tension is resolved through engineered controls, not through brute force. And the first, most critical control is the learning rate.
Okay, so to clarify for everyone, the learning rate dictates how big of an adjustment the model makes to its internal knowledge, its weights, during the training process.
Correct. When Whisper was initially pre-trained on that massive 680,000-hour data set, it used a relatively large learning rate, and that was necessary. It needed to take these aggressive, big steps to explore the vast, high-dimensional solution space of all possible acoustic and language rules.
It had to find a good starting point in a huge, unknown territory.
Exactly. But during fine-tuning,
We do the opposite.
we do the complete opposite. We drastically reduce the learning rate. We're often moving from initial rates of around 1E3 or 1E4 all the way down to rates as low as 1E5 or 5E5.
That's a huge reduction. Why is slowing it down so essential?
Think of the model's knowledge as a landscape of hills and valleys, where the deep valleys represent good solutions with low error.
Yeah.
The pre-trained model has already found a very deep, very wide valley. That's the general ASR solution.
Okay.
If you come in now with the large learning rate, your small, specific data set will basically convince the model to take a giant leap entirely out of that good general valley and fall into a tiny specialized pit.
Which is the overfitting scenario we just talked about.
That is exactly the overfitting scenario. So the extremely small learning rate acts like a highly sensitive braking mechanism. It ensures the model only makes these tiny incremental adjustments.
Like very small, careful steps.
Exactly. It makes tiny adjustments, like turning a dial just a fraction of a millimeter, that allow it to just nudge itself toward a local refinement within the existing good valley. Your small data set is sufficient to find that tiny optimal corner customized for your voice without ever challenging the fundamental, globally correct structure the model has already learned.
So that's the first key to preventing catastrophic forgetting.
It is. The training recipe itself enforces this specialization. It's not some happy accident.
It's entirely intentional.
It is. And furthermore, this controlled adjustment isn't even uniform across the entire model architecture. And that leads us to the next critical concept, which is layer dynamics.
Okay, so tell us about the separation of duties within the Whisper architecture when you're fine-tuning.
Whisper is an encoder-decoder transformer. The early layers are responsible for low-level processing, and the late layers handle all the high-level context.
So let's start with those early layers, the foundation of the encoder. What's their job?
The early encoder layers are dedicated to processing the raw acoustic input. They convert the audio into a Mel spectrogram, and then they identify basic, universal acoustic features. Energy levels, pitch changes, fundamental phone characteristics.
And this is irrespective of who is speaking.
Totally irrespective of the speaker's accent. During fine-tuning, these early layers change minimally. We're talking maybe a 0.1% to 1% weight change. They preserve the general knowledge that defines what speech is. You don't want to redefine how a microphone captures sound.
So they stay universal.
Yeah.
The core understanding of sound waves and frequency separation is basically left untouched.
Precisely. Now, if you move to the later layers, especially the top encoder blocks and the entire decoder stack, this is where the linguistic intelligence lives. The self-attention mechanisms in the decoder stack are responsible for context, for grammar, for vocabulary, and for mapping those acoustic features to specific language tokens.
And these are the layers that are most open to customization.
They undergo the most significant changes, typically a 5% to 30% weight change.
Why is that?
Because this is where your specific knowledge needs to reside. Fine-tuning tells the model, hey, when you hear this specific acoustic pattern, which is the listener's accent and voice map, it's specifically to this unique technical term like gRPC, or to the specific code-switched Hebrew word, and structure it with this grammatical pattern.
So the model preserves its ability to recognize speech in general, but it refines its output vocabulary and its spelling to match your specific domain.
That's it. It's an incredibly efficient process. You're only modifying the parts of the brain that handle specialized language, and you're leaving the universal sensory and motor skills completely intact.
And we can enforce this preservation even more strictly now with techniques like LoRa.
Yes, low-rank adaptation.
LoRa has pretty much taken over the model customization world lately. How does it provide an even cleaner solution to this catastrophic forgetting problem than just, tweaking the learning rate?
LoRa is really the ultimate elegant architectural solution. Instead of modifying the massive pre-trained weight matrices, which always carries a risk of corrupting that foundational knowledge, LoRa completely freezes those original weights.
So all 680,000 hours of knowledge are locked in place, untouchable.
Yes. LoRa then introduces these small auxiliary adapter matrices alongside the original weights. When the model processes input, it simultaneously runs the data through the massive frozen weights and these tiny trainable LoRa adapter matrices.
And then it just adds the results together.
The output of the adapter matrices is added to the output of the frozen weights. So your personal knowledge is entirely contained within these tiny additive matrices, and the base model is never physically modified at all.
That's really clever.
It gives you three massive advantages. First, you get perfect preservation, so no catastrophic forgetting. Second, it's highly efficient training because you're only training a tiny fraction of the total parameters. And third, it's great for deployment efficiency. You only need to store the massive frozen model once, and then you can just swap out these tiny adapter files for different users or different domains.
LoRa is genuinely the pinnacle of smart engineering for this kind of personalization. It just solves the architectural puzzle perfectly. But let's talk about the payoff. Why is this fine-tuning effort actually worthwhile for the individual user beyond just academic elegance?
Because it delivers very real practical performance gains, especially for users who are relying on less powerful hardware. And this is what we call the crossover effect.
Okay, explain the crossover effect for someone who only has a small GPU at home.
Right. So Stock Whisper comes in different sizes: tiny, base, small, medium, large. The smaller models are faster, obviously, but they have a naturally higher baseline word error rate because they just have less capacity. For instance, Whisper Small might have a whir of 12% on your voice. Whisper Medium might have 8%. But that medium model requires substantially more VRAM and is much, much slower to run.
So the goal then is to get the small model to perform like the medium model, but without the computational cost.
Precisely. The smaller models have more room to improve, in a way, because their error landscape is less optimally defined than the massive, highly trained large models. So by fine-tuning that Whisper Small model on 10 to 20 hours of your gold standard data, you're essentially correcting its most glaring deficiencies related to your specific voice and vocabulary.
What's the result of that?
We often see a fine-tuned Whisper Small achieving a 6% to 8% IVR per TRR on the listener's specific domain.
So it functionally matches or even beats the stock performance of the slower, larger Whisper Medium model.
Exactly. It's a huge practical win. You're achieving high-level accuracy locally on a small, fast model that runs efficiently on modest consumer hardware.
And this customized knowledge, it solves those specific pain points that generic models just can't handle, like the Hebrew-English code switching patterns we mentioned earlier.
Oh, code switching is a nightmare for generic ASR. A complete nightmare. Stock Whisper is trained to identify one language for transcription at a time. So when it hits a Hebrew word mid-sentence in an English context, it often defaults to phonetic transliteration using English rules.
Which results in just nonsense words or garbled spelling.
It's technically an accurate transcription of the sound, but it's a completely useless transcription of the meaning.
Right.
So fine-tuning teaches the model the listener's specific code-switching lexicon. It learns to recognize that, for example, when spoken in an English cadence, a specific acoustic pattern should be mapped to the correctly spelled Hebrew term or proper noun rather than trying to cram it into the English vocabulary space.
And the final piece of that puzzle, the specialized vocabulary. This seems to be the source of most of my daily transcription errors.
For most technical people, it is. Technical terms, Kubernetes, PyTorch, ROCM, Tailscale, they're often rare, or they're homophones that just confuse stock ASR. They are the 1% of words that cause 90% of the frustration.
I believe that.
Fine-tuning specifically targets these domain-specific terms. Because we're providing the model with dozens and dozens of correct examples of these terms in context, we routinely see a 50% to 90% reduction in mistranscriptions for that specific jargon.
Wow, 50 to 90%. So this really proves that fine-tuning isn't just some marginal improvement. It fundamentally shifts the model's reliability from general competence to personal proficiency. It solves the exact errors that make a stock model unusable in a specialized workflow.
It's the difference between a neat toy and a professional tool.
Okay, so we firmly established that fine-tuning is the optimal path. Now we need to detail the actual hard work, the data collection. This is often, 80% of the effort? And if you do it wrong, the rest of the work is basically wasted.
You're absolutely right. Data preparation is the bottleneck, and it's the crucial differentiator. First, we need to move beyond that minimum proof of concept of 30 to 60 minutes. That's just not enough.
So what's the sweet spot for a really deep single-speaker adaptation?
The recommended volume is 10 to 20 hours of high-quality, diverse audio. 2 to 5 hours is enough for a noticeable improvement, for sure, but 10 to 20 hours allows for robust domain adaptation. That means the model will generalize well to new, related topics within your field.
That 10 to 20-hour commitment is pretty substantial. If I only have a limited amount of time, is it better to aim for 10 hours of absolutely perfect transcription or maybe 20 hours of slightly messier, faster transcription?
Quality absolutely 100% trumps quantity here. 10 hours of a meticulously curated, accurately transcribed data, the gold standard, is far, far superior to 50 hours of sloppy data.
Why is that?
The model learns from its mistakes. But if the ground truth transcription you provide is faulty, the model is essentially learning faulty instructions. Your word error rate may actually increase because you're actively confusing the model about basic word-to-sound mapping.
That really emphasizes the critical nature of the human review process. It has to be perfect.
It has to be as close to perfect as you can get. And beyond just manual review, achieving that gold standard efficiently involves using specific tooling for transcription alignment. You shouldn't be manually time-stamping every single word.
No, that would take forever.
It would. You should use automated alignment tools like Gentle, or there are specialized scripts that leverage existing ASR models to predict the timestamps for you.
So the process is record your 20 to 30-second chunks, transcribe them quickly, and then run an alignment tool to precisely match the text to the audio waveform.
Correct. The alignment tool breaks that transcription down to the subword or even phone level and ensures the model knows exactly which moment in the audio corresponds to which character in the text. That precision is vital for minimizing error and maximizing the learning you get during fine-tuning.
Okay, now let's get into the really low-level technical requirements.
Yep.
What must you ensure about your recording setup?
There are 3 non-negotiables: sample rate, channels, and format.
Let's take them one by one. Sample rate.
Must be 16 kilohertz. Whisper was trained exclusively on this rate. If you record higher, say at 48 kilohertz, it's just going to be downsampled, often inefficiently. And if you record lower, you're losing necessary acoustic information the model expects.
Okay, 16 kilohertz channels.
Mono, always mono. Stereo channels just introduce unnecessary complexity and potential phase issues that can confuse ASR models. They don't help.
And finally, format.
Use a lossless format. WAV or FLAC is best practice. These preserve the acoustic signal without any compression artifacts, giving the model the cleanest possible features to learn from.
And we absolutely must respect the 30-second constraint. Why is this a hard architectural limit in Whisper? What's going on under the hood?
This is a deep architectural constraint, and it's tied to how transformers process information. The attention mechanism within the transformer model, which is what allows it to link every word to every other word in the sequence, scales quadratically. That's O of n squared with the input length.
An O(n) squared means if you double the length of the audio, the computational cost increases fourfold.
Exactly. It gets expensive very, very fast. So to manage memory and complexity, the MEL spectrogram input that Whisper uses is fixed to specific dimensions. A 30-second chunk is the practical limit imposed by this quadratic scaling.
So what happens if you try to feed it a 45-second clip?
The training script will either just truncate the last 15 seconds, so you're wasting data, or it might outright crash because of a memory overflow during those attention calculations.
So while we often hear 8 to 12 seconds is efficient for training, the listener's preference for 20 to 30 seconds is actually beneficial as long as they stay under that hard limit.
It is excellent. That 20 to 30-second window captures complete natural sentences. It captures entire narrative arcs and crucial prosody, the rhythm and intonation of your speech.
Which is important for context.
It's critical for context. Teaching the model how you structure complex technical thoughts and the context between words requires that longer duration. It really maximizes the benefit of the language modeling component of Whisper.
Now let's circle back to that counterintuitive data science truth we briefly touched on. The signal versus noise trade-off. If my plan is to use this model in noisy meetings, Shouldn't I record my 10 hours in a cafe or with background noise?
Absolutely not. This is one of the most common and damaging mistakes people make in custom ASR projects. The counterintuitive truth is that you should primarily record clean, high-quality audio. About 80% of your data should be recorded in a quiet room with a quality mic.
Challenge that for me. If the model is going to be deployed in a messy environment, shouldn't it train in one? It feels logical.
It feels logical, but no. Because training in a messy environment means the model is learning from uncontrolled noise. Every cafe recording, every street recording has a unique, specific noise profile. The model, which is trying to generalize, will fail to isolate your voice features because it keeps associating your speech patterns with thousands of wildly varying acoustic backgrounds.
So it starts to overfit to specific noise patterns instead of learning general robustness.
That's exactly what happens. So the right way to do it is to train the model to understand the pure signal of your voice first, and then you teach it how to ignore noise systematically.
Through controlled data augmentation.
That's the key. After you've collected your 80% clean audio, you programmatically apply augmentation techniques to the remaining data, or you can inject them into the training pipeline dynamically.
Can you give some concrete examples of what those augmentation techniques look like?
Yeah, we move far beyond just simple white noise. A big one is room impulse response convolution, or RIR.
What does that do?
You simulate different room acoustics by convolving your clean audio with these RIRs. This mimics echo, reverberation, room shape. It's crucial for teaching the model to handle diverse meeting room environments.
Very clever. What else?
Then there's spectral augmentation. Techniques like spec-augment will randomly mask out specific time steps or frequency bands on the spectrogram. This forces the model to learn to fill in the missing data from context, which makes it really robust against things like audio dropouts, bad connections, or just momentary acoustic interference.
It's like training with missing pieces of the puzzle.
It is. And finally, you can do things like VAD simulation, voice activity detection. You simulate imperfect starting and stopping points, so the model has to learn to distinguish between non-speech sounds and the actual beginning of your speech.
So this whole structured approach ensures the model learns to filter any type of noise, not just the noise from one specific cafe you happen to record in.
Exactly. You keep the gold standard signal pure, and you introduce the variability programmatically. This ensures the model's robustness generalizes beautifully to real-world deployment.
Finally, let's address the highly nuanced detail of personalized punctuation. This is something I struggle with. Punctuation is often a matter of personal style, my habit of using dashes constantly, for example, or unique comma placement. Can fine-tuning the ASR model teach it my stylistic preference?
It's extremely difficult. I would say it's bordering on impractical to try and force stylistic punctuation changes through ASR fine-tuning alone.
Why is that?
Well, integrated ASR models like Whisper do learn punctuation from acoustic cues, pauses, pitch drops, that sort of thing. But punctuation marks are statistically very sparse in the audio data compared to actual word tokens. Trying to teach a personal style can just end up confusing the core acoustic-to-word mapping.
So what's the practical, robust engineering solution for this?
The solution is decoupling. You should fine-tune your ASR model to achieve the highest possible accuracy on the words. First, focus strictly on minimizing the word error rate. Then, you introduce a separate punctuation restoration model that acts as a post-processor.
So it's a two-stage pipeline. The fine-tuned ASR provides the raw stream of words, and then a second model comes in and cleans up the prose.
Yes. You would train a dedicated punctuation model, maybe based on a small language model architecture like Full Stop, and you'd train it using a massive corpus of your existing written work.
So my emails, papers, notes.
Exactly. Ideally 50,000 to 100,000 words. This separate model learns your idiosyncratic stylistic habits without impacting the ASR acoustic processing at all. It learns that in your prose, a long clause often requires a dash, not just a comma.
That's a very clever solution. The ASR handles the sound, and a separate language model handles the personalized style.
It maximizes the accuracy and the control you have over the final output, and it ensures that the final transcript truly reflects both your voice and your writing style.
All right, so that brings us to the finish line. Deploying your bespoke ASR.
Right. We now have a fine-tuned, personalized Whisper small model. It's an efficient, highly accurate asset. The final crucial step is deployment, and we need to make sure we leverage the listener's specific hardware as efficiently as possible.
The listener mentioned they're using an AMD GPU and they're looking for efficient local inference, specifically to avoid high server costs. So this means we need to talk about formats that are optimized for speed.
Absolutely. The standard PyTorch format, safe tensors, is really only suitable for training and validation. It's just too slow for production inference. We have two major optimized formats we need to discuss: CTranslate2 and GGUF.
Let's start with the desktop GPU environment. Which format is the clear winner for local, fast inference, especially with AMD and ROCm hardware?
The recommended choice for desktop production inference is CTranslate2. This is the backend that powers highly efficient implementations like faster Whisper.
And what gives CTranslate2 its, 3x to 4x speed advantage over the original PyTorch model?
It's highly optimized for rapid inference through several key techniques. First, it performs very aggressive weight quantization. It typically reduces the model weights from floating point 32 down to 8-bit integer without a significant loss in accuracy.
And that reduces the VRAM footprint and memory bandwidth requirements.
Drastically. Second, it utilizes things like kernel fusion and specialized compute graph optimization, which ensures that the matrix multiplications, the core of the transformer, are executed as efficiently as possible on the target hardware.
And what about for the AMD ecosystem specifically?
CTranslate2 and Faster Whisper have historically maintained really robust and optimized support for ROCm, which is AMD's platform. While the AMD ecosystem can sometimes be a bit challenging with bleeding-edge AI models, CTranslate2 is a mature, production-proven framework. It reliably leverages the specialized capabilities of AMD GPUs, and it offers that critical speed boost and memory efficiency you need for 247 local use.
Okay, so CTranslate2 for the desktop GPU. Now, what if the listener wants to use this same model on their mobile device, like their OnePlus Nord 3, where they're running on the CPU?
For CPU inference, for edge devices, for mobile deployment, the format of choice is GGUF. This is the successor to the original GGML format that was developed by the team behind Whisper.cpp.
And what makes GGUF superior for these resource-constrained CPU environments?
GGUF is specifically designed for CPU efficiency. It uses a memory-mapped structure, which means the entire model doesn't need to be loaded into RAM at once. It just reads segments directly from disk as it needs them.
So it can run on systems with much less available memory.
Much less. Furthermore, it supports a whole variety of low-bit quantization types, Q4, Q5, Q8, that are optimized for CPU instruction sets. This makes inference faster and enables the model to run on devices that simply couldn't handle the larger FP16 size.
So the overall deployment strategy is pretty clear then. You fine-tune the small model once in the standard PyTorch format. Then you convert that single model to CTranslate2 for blazing fast desktop GPU inference, and you also convert it to GGUF for portable, efficient CPU inference on your mobile devices.
Exactly. One training effort yields two highly optimized deployment paths covering all of your target environments.
Now, the listener was rightly concerned about the ongoing cost of using the model continuously. Let's compare the cloud costs against this local solution we've just detailed.
This comparison is crucial because it really highlights the cost-effectiveness of doing this kind of personalization. If you use a serverless platform like Replicate or Modal, they offer excellent convenience, but they charge you per second of inference time.
And if you're running speech-to-text continuously throughout a heavy workday, those seconds add up really fast.
They do. A small workload might be, $5 to $20 a month, but continuous heavy use will easily escalate your costs into the hundreds of dollars monthly. Even a predictable CPU-only cloud VPS might cost you $35 to $50 a month for pretty slow, predictable performance.
But the real winner for a solo user who's running this frequently is the local deployment on their existing hardware.
Unquestionably. Once the initial hardware investment is made, which the listener already has, the ongoing cost for an individual running STT continuously is essentially just the marginal cost of electricity.
How does that work out to?
We estimate an existing efficient GPU server running 247 for this workload costs only about $15 to $30 per month in electricity.
That's a massive difference, tens of dollars versus hundreds. And on top of that, it offers instant inference, which is crucial for real-time transcription, plus full privacy and offline capability.
It provides the trifecta of cost, speed, and privacy. And for secure access, you don't even need complex firewall configurations. Tools like Cloudflare Tunnel or Tailscale allow you to securely expose your local ASR API only to your own devices, making it function like a private cloud service, but with none of the overhead.
This local, personalized ASR is truly one of the most practical and cost-effective AI tools an individual can build for themselves.
To really finalize this point and reinforce the power of transfer learning, let's just look at the ultimate end of the ASR spectrum, mission-critical enterprise deployment.
Right. We're talking about sectors like air traffic control, legal proceedings, high-end medical transcription, where a 1% error reduction can literally save lives or millions of dollars.
Yeah.
Do these organizations with effectively unlimited R&D budgets train their ASR from scratch?
They absolutely do not. The largest, most complex organizations in the world recognize that the foundational knowledge, that 680,000 hours, is just too valuable and too expensive to replicate. They rely entirely on a highly specialized fine-tuning strategy.
So what does that enterprise fine-tuning path entail?
It involves three key components. First, they collect massive amounts of custom domain-specific data, often 50 to 100 hours or even more, all of it certified by human experts. Second, they fine-tune existing state-of-the-art models, like highly customized versions of Nuanced Dragon or similar proprietary systems, using the same strict layer dynamics and learning rate controls we talked about.
And the third, crucial component, the human in the loop.
Exactly. Heavy reliance on human transcriptionist review and continuous correction. ASR is seen as an efficiency engine. It's an assistant that speeds up human work, not a fully autonomous system. The most critical final accuracy gains come from that continuous human feedback being looped back into the model.
And the staggering thing is the accuracy difference is ultimately minute.
It is. A commercial off-the-shelf ASR might hit 5% ER. A custom multi-million-dollar enterprise implementation might achieve 3% to 5% ER. That final 2% accuracy gap from 5% down to 3% requires years, millions of dollars, and the continuous oversight of dozens of experts.
It perfectly illustrates that even at the highest level of complexity, fine-tuning is the optimal, pragmatic engineering approach. No one starts from scratch.
So what does this all mean for you? We've established, I think, pretty definitively that training ASR from scratch is an impossible multi-million-dollar endeavor that results in unusable gibberish because of catastrophic overfitting. The elegant, robust engineering solution is transfer learning.
The path forward is highly effective and efficient. You collect 10 to 20 hours of clean, 16 kilohertz mono audio using those 20 to 30 second chunks to capture context and prosody. You use programmatic data augmentation to teach robustness, fine-tune the small model with a tiny learning rate and LoRa adapters, and then deploy it locally using C-Translate 2 for desktop speed and GGUF for mobile portability.
And here's the final provocative thought to anchor all this knowledge. The real usability barrier for an individual user isn't achieving 5% ER instead of 10% ER. It's ensuring that the model doesn't make those embarrassing repetitive mistakes on the 20 technical terms you use every single day.
The practical gain from fine-tuning a small or a tiny model, eliminating those constant, frustrating errors on your keywords and your accent, that far outweighs the pursuit of that final multi-million-dollar 2% of accuracy.
This makes the local, personalized ASR approach, built on the back of transfer learning, one of the most high-impact and cost-effective AI investments an individual can make today. You now possess the knowledge to execute this project with the precision of a seasoned machine learning engineer.